of the day will be by Kirsten Wickelgren, and she is going to give her, I guess, third talk on A1 enumerative geometry.
Thank you. Thanks to Jay Shaw, we have a correction from this morning. So we had these residue maps used to define the sheaf K. Milner-Witt or K. Milner. And it's true that eta commutes with these residue maps, and this defines, together with the other property, the map uniquely, but we can't have eta go to eta because that's not decreasing the degree by 1, and eta goes to 0. So this is true. The first one is true. Actually, they're both true, but the correction is the second one. So we do have now sheaves K Milner-Witt. And GW. And the sheaf property means that for any map, in particular, if we had an inclusion of fields K into L, we get a map spec L to spec K. And we could apply GW to it, and this is restriction or base change tensoring with L over K of bilinear forms. But we also saw that these were stable homotopy sheaves, and so there should be transfers. And we want to use them. For instance, they showed up, this trace or transfer for field extensions. So let's take K and L, finite extension of finite type schemes over K. So we're going to this leads to maps in the other way, not from the Grothendieck-Witt group of K to the Grothendieck-Witt group of L, but transfers L over K in the other direction. And there are a couple types of transfers. For instance, in Morel's book, there's a geometric transfer, which is the prettiest, and it's the one we'll define. But then you precompose with multiplication by one of those brackets to define a cohomological transfer. And the advantage of that is this will depend on a chosen sequence of generators. And you can get rid of that here. And if you use twisting data, you can get an absolute transfer. And in the case where K to L is separable, they're sort of in twisted Grothendieck-Witt groups, for the kinds of extensions we saw yesterday where K to L was separable, there's a canonical way to untwist. And so these two agree, and it was this, so for these two, explicitly we took beta V cross V to L, and the transfer L K of this was we view V now as a K vector space, and we compose with the transfer from Galois theory, the sum of the Galois conjugates. And this is when K and L is separable. Let's show that we have this structure. So we'll do the geometric one. If L is K adjoin Z over some polynomial, so we've chosen a generator, we get an induced map from spec L to P1K. And we can form a backwards map by crushing, so this is a closed immersion corresponding to this point, by crushing everything but that point. Oh, it's still over K. And we saw this morning that this was P1L, and so we can apply, now we can apply K Milnor-Witt 1 to this map, and we'll get is a map which would be the geometric transfer. We call that transfer geometric, like we were seeing. So let's wave hands about the rest of the transfer story and congratulate ourselves on having some transfers. Okay, so the sort of the projected finale of this morning was going to be adding bilinear forms to Chow groups for the purposes of having a new tool in enumerative geometry. But let's review Chow groups. So we'll take X, a smooth K scheme, and we'll let Xi be the set of codimension I reduced irreducible subschemes of X. And then Chow I of X is the quotient of the free abelian group on Xi over an equivalence called rational equivalence. And that's the equivalence relation generated by if you take subvarieties of X cross P1, we say that the fiber over 1 is equivalent to the fiber over 0. And these are useful in enumerative geometry. They've got Chern classes, push forwards, pullbacks, ring structure. And this lets us do ring structure coming from intersections, intersection theory, and get some machinery to help out with enumerative questions. Oriented Chow groups they're also known as Chow-Witt groups. They are, let's denote them like so. They're formal sums of Z in Xi, but together with a bilinear form. Let's give a definition. So there's a formula for a smooth scheme due to Bloch that says that the ith Chow group, in addition to being a motivic cohomology group, is the Nisnevich cohomology of X with coefficients in Milnor K theory. And Barge and Morel, with an explicit complex, introduced oriented Chow groups, and we can define them, or they define them as the Nisnevich cohomology of X, this time with coefficients in K Milnor-Witt of I. And this can be computed by a complex as in Morell's book, where we're still interested in combinations, in formal combinations of codimension I schemes, but we take the Grothendieck-Witt group of the function field, and we're going to do a twist as well. So the Z has a generic point, and we could take the highest wedge power of the tangent space to X at Z, and it fits into a complex with these modifications of the residue maps we were looking at previously into K Milnor minus 1 of K of Z with the same determinant. And it gets hit from the analogous thing with K of 1 and Z and X I minus 1. Elements from that, we get that elements of oriented Chow are formal combinations of a subvariety of codimension I and a bilinear form over K of Z. And then there's structure here. So Feazell developed ring structure and push forwards and did a lot of work on this. And in the context of enumerative geometry, Mark Levine works with these. And so there's pullbacks. So if we have F, X to Y, we have a pullback in the other direction. We can twist these groups as well. So I see, well, let me say pullbacks, they're push forwards, and there's a non-commutative ring structure. Let me define these twists, and then in some sense we should define how to do twisted Chow so that we can do push forwards correctly. Well, let's try to squeeze that all in. K, so E is a field, finite type over little k, and we take K Milnor-Witt I of E twisted by lambda one-dimensional E vector space. Then what we can do is take K Milnor-Witt I of E and tensor over E star acts on K Milnor-Witt I through the Grothendieck-Witt group, the bracket E, and we can also act on the non-zero elements of the vector space, which defines these groups in this complex. We could then also twist. This leads to Chow groups, oriented Chow groups, with twisted coefficients, which is HIX K Milnor-Witt I twisted by L, where L is a line bundle on X. So then we have a push forward if F X to Y is proper, and the dimension of Y minus the dimension of X is R, then we have a push forward from oriented Chow I of X and coefficients of the canonical line bundle of X over K. So this is the determinant of the tangent bundle of X, tensor with any pullback of a line bundle from F to the oriented Chow minus R of Y omega Y over K tensor L. So this was going to be the finale of the last lecture, because here we've got some machineries to start counting together with a bilinear form, and this bilinear form is acting a little, is acting like an orientation. And I think one could get poetic about that so that was, I'm going to say that is exciting. And that's the end of lecture 2. So lecture 3, we were going to be more concrete about the degree. So we're going to do the degree via local degree. So let's go back to algebraic topology. If we've got a map, f Sn to Sn, let's say it's smooth, we've got a degree of f. We can pick a regular value, so pick y and Sn with f minus 1 of y, a finite set of points x1 through xn. And the degree of f is the sum of local degrees. The first lecture, we did this small ball definition of a local degree, and there's a calculus or formula for the local degree. So we can choose coordinates. I wish I hadn't chosen my x and y like this. We're going to make this p and these q. So we can choose coordinates x1, xn near qi, and y1 through yn near p, compatible with orientations. And then f looks like a function from Rn to Rn, and we can deform its Jacobian. So then the Jacobian of f is the determinant of the matrix partial fi partial xi, and the degree, the local degree, is 1 if the Jacobian is positive, and it's minus 1 if the Jacobian is negative. And we could use this to concretely compute the degree of a map. So in A1 algebraic topology, Lan and Morel said, instead of just remembering the sign, like the signature of the Jacobian of f, let's remember the entirety of the Jacobian of f. So take f from P1 to P1 over field K, and take y or P k rational point of P1, and let's say f minus 1 of P is Q1 through Qn. Then we can define the degree of f as the sum of the Jacobian of f at Qi, and this doesn't depend on P. So we can definitely calculate that.
Is the bilinear form like V transpose Jacobian W or something? Like, what is it?
It's a one-dimensional form. So it's just you multiply by the value.
Got it.
Like you take x, y, one-dimensional vector space. Yeah. So the degree being sums of local terms that you could calculate with a determinant works for higher dimension 2. So a proposition, the global degree is a sum of local degrees. So if, let's,
It's a little blurry now.
what should I do?
I'm not sure. Keep going.
I'm all for that. Okay. So let's take f pn to pn, say finite for safety, and such that f minus 1 of a big an, so let's say we have a favorite copy of an sitting inside pn, is let's say an is going to map to an, then we have an induced map f bar from pn over pn minus 1 to pn over pn minus 1, and the degree of f bar is sum over q and f minus 1 of p for any p, a, and k of a local degree of q of f, and where this local degree, we could define it with those balls like we did on the first first lecture. So if we assume that f is finite, there are finitely many of these q's, so we can stick, so we're degree q a1 of f is the degree of the following map of the composite. We can choose an open set such that q is the only element mapping to p, and then we have a well-defined map and since this is k-rational, we saw that this is pn over pn minus 1. This is purity here. It's the Tom space of the normal, or the normal bundle is then the tangent bundle. And then if this is k-rational, that's illegible. So if k of q is k, then this is also pn over, it's also a sphere. And we can take the composite of that. Thanks. And if it's not, kind of the Hatcher proof of this result means that you could also, we've got a collapse map, pn minus 1, mapping to pn over pn minus q, mapping to that. So in general, so the composite of this map is if you've got a rational point, and if otherwise, you can take this. And then we've got, so that's a definition of the local degree in terms of the global degree, analogous to taking boundaries of balls. And then we've got some facts, which is that if f is a tall at q, then degree q a1 of f is the, let's say, and, well, we don't, depending on what we mean by transfer, we don't need this hypothesis, but to do the explicit composition with the Galois theory trace, let's assume this is separable, is the transfer of the Jacobian of f at q. Okay, so we could use that to compute the degree. except we are missing something. So
Kirsten?
yes.
In the case of P1 to P1, do we have an étal assumption there? Is that implicit in?
Yeah, so we were also, we had to assume étal, thanks, actually, yeah. So, and we need this to be non-zero, so that it's actually a non-degenerate form. And so that is what we're missing, so question, what if Jacobian of f equals 0? And there's a beautiful answer from the late 70s to that question when you have a map over R. So answer is the Eisenbud, Levine, Kim, Shiash, Billy signature formula. And what it says is that in the, so let's take f Rn to Rn, 0 goes to 0, is an isolated 0, so there's a little ball around it that has no other zeros. And it says that the local degree of f at 0 is the signature of a quadratic form that we can call omega EKL. And so this formula is from the 70s. It's great and it's beautiful. I have nothing to do with it. But for this presentation, I'm following joint work with Jesse Cass, and so I'll write Jesse's name up there as soon as possible. Okay, so omega EKL is bilinear form over R. So is a bilinear form on the vector space, let's call it Q, where we take R x1 xn, localize at 0 over f1 fn. Because this is isolated in its fiber, this is a finite dimensional R vector space, and the Jacobian, while it may live in the maximal ideal x1 through xn, the Jacobian of f is in Q, and we can pick any eta from Q to R, R linear, such that eta sends the Jacobian to the dimension of Q. Then we can make the bilinear form. So omega EKL is the form Q cross Q to R, which sends two functions AB to eta of A times B. Eisenbud asked, he said this could be used, the whole form could be used as a degree. So a question of Eisenbud is omega EKL could be a degree, not just its signature. Does this have an interpretation as an algebraic topology? And this is around 1979, which is before A1 homotopy theory. But the answer is yes, it does. It's the local degree in A1 homotopy theory. So the degree of, so omega EKL could be a degree, even replacing R with a field K, with some different field K. We can still do this construction, replacing R with K, and then we get a bilinear form over K. And the local degree is the form constructed like that. So a project is to get rid of the hypothesis. So this will work for any rational point, but remove the K of x equals K hypothesis. So let's do an example. Let's compute this form, the omega EKL. So this omega EKL of the map f of x equals x squared. So we make our Q. We have k adjoin x over x squared. And we don't need to localize it 0 because it's already, it's the only preimage, 0 is the only preimage of 0. The Jacobian of f is 2x. So we can choose eta from kx over x squared to k, and we need to send 2x to the dimension of q, and a basis for q is 1 and x. So this has to go to 2. And then we could send 1 to whatever we want. And the claim is that that's not going to affect the isomorphism class of the form because, for instance, this is well defined. Let's see that. So we could make a Gram matrix of our form, putting the values of the form on 1, 1, 1, x into a matrix. And on x, we know we need to send x to 1. And x squared is 0 in the ring, so we send that to 0. And then no matter what we send this to, we can make a basis change. We can just add x times something to make this 0, and that would correspond to the choice of this linear function. So we get that the omega EKL is represented by this matrix, which can be diagonalized to be diagonal with 1, 1, and 1 minus 1. Yeah, so there's a replacement for this. So this is if for this description to hold, we are assuming that the dimension of Q is not divisible by the characteristic of K. So we said we were going to do this over R, and then we'll do the same thing for any field. And we need this hypothesis now extra. But if it does, so otherwise, you can use a distinguished Sockle element instead. Use a distinguished Sockle element in place of the Jacobian. Thank you. Okay. So yes. We've got a way to concretely calculate degrees of maps from Pn over Pn minus 1 to itself. So here's an enumerative application. Let's call this A1 Milnor numbers. And this is also joint with Jesse Cass. Let's think about the classical Milnor number. One possible definition of the Milnor number is that it counts nodes. So let's also define a node. Say a point P on a scheme X is a node if after base changing to the separable closure and looking at all of the pre-images, we'll just say if after base change to KS, the completed local ring of X at P is a standard node. Namely, we've got x1 squared dot 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 plus xn squared plus potentially higher order terms. So that's a node. If you take a hypersurface, so let's let X be a hypersurface. X equals the scheme determined by a single equation. We could let's see. And if we move the equation a little bit and we were at some sort of complicated singularity, that singularity will bifurcate into nodes. So let's let P and X be a singularity, perhaps it's complicated. When you move X a little bit, so as X is perturbed in a family, P bifurcates into nodes. Let's be more specific about this. So we have, say this is in n variables. If we've got f of x1, xn equals 0, that's our original x. And we could add some other terms. The terms we're going to add are linear, so we could make any choice of a1, a2, x2 plus dot 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 plus an, x to the n is t. So for any a1 through an, we have a family of varieties of hypersurfaces. Index parameterized by t. So for each t, we get a hypersurface. We're fixing them for parameterized by t. And one definition of the Milnor number is that in any such family, you will have the Milnor numbers worth of nodes. So let's say k equals c. So it's a result of Milnor. K equals c for any sufficiently small A1 through AN, this family contains a fixed number, mu of p, nodes, where mu of p is the Milnor number. If you want to know where one has nodes, we can look at the gradient and see where all of the coefficients of the linear terms vanish, so that we just have x1 through x squared plus higher order terms. So we're looking for for zeros of the gradient. So we're looking at the inverse image of the gradient. So we're picking up something, we're picking up the degree of the gradient. So another possible definition among many of the Milnor number is that this is the topological degree of the gradient of f evaluated at p. But when k is not c, nodes have interesting information. So when k is not algebraically closed, nodes contain certain arithmetic data. For example, so k equals r, we have the node x squared plus y squared equals 0. It's just the dot, and x squared minus y squared equals 0 are two lines. This is the non-split node, meaning the tangent directions are not defined over the ground field. And this is the split node. We can use the A1 degree in place of the topological degree and do the same argument that we're trying to count the zeros of a gradient, and we will count them, and it will naturally pick up something about the node. So we'll define the type of a node. The type of a node P, it can be defined as the A1 degree of the grade P in the hypersurface F equals 0. Or it's a node is cut out by an equation, is the degree at P of grad F. If over so when equivalently let sort of choose a preimage of P after phase change to K of P, then the node is cut out by then the local ring, the completed local ring. Just call it P again. We've got KP x1 xn over A1 x1 squared plus A2 x2 squared plus AN xn squared. We can have cross, sorry. well, let's say, we'll do an example so that I don't have to take a big determinant. Let's suppose that we have A1, that we're cut out by A1 x1 squared, A2 x2 squared, dot, 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 an xn squared plus higher order terms. Then the type of P is the trace from K of P down to K, and this is always a separable extension, actually. That's in SGA, so always separable extension of 2 to the n, A1, A2, dot, dot, AN. So for example, these nodes where you've got x squared plus y squared, like for plane curves, so the type of the 0, 0, the one node in x squared plus a y squared is bracket A. It's picking up, in this case, the field of definition of the two tangent directions for the node. And when it's not rational, it picks up the trace of its field of definition with the two tangent directions. So it's some geometric arithmetic information about the node, about fields of definition for the node and its tangent directions. Okay, so then the same proof applies. So if we say, let's definition P a hypersurface singularity, we can define the A1 Milnor number of P to be the degree at P of the gradient of F, and then it follows that for a generic A1 AN, the sum over P nodes in the family of the type of the node, the field of definition, let's not call this P. Our nodes will now be X. So the fields of definition of X, the fields of definition of their tangent spaces, it always has to be this fixed element of the Grothendieck-Witt group of K, which is the Milnor number of your singularity. And this is joint work with Cass. Let's do an example. Let's take f of xy equals y squared minus x cubed. And let's first compute the A1 Milnor number, so we can take the gradient of f, and that is minus 3x squared 2y, and we can take the Milnor number of 0, so this is the A1 Milnor number, it's the degree at 0, the local degree of the gradient of f. Since these two variables are split apart, this is actually a smash product of two other maps of spheres, and we get the degree at 0, bless you, of x goes to minus 3x squared, and the degree at 0 of y goes to 2y. This y goes to 2y, that's étal, so we know that the degree of that is just 2 in brackets. the x goes to minus 3x squared, let's assume that the characteristic of k is not 2 or 3, then it's a very similar computation to before, or if you like, it's just post-composing with multiplication by minus 3, which also multiplies the degree. So we get 1 plus minus 1. But one of our relations was that minus 6 plus 6 is 1 plus, is the same. So this is this element h, this hyperbolic form. So let's look at that in a family. So there was the Milnor number side, and let's look at families. So we can also take the family parameterized by t, so that it looks just like an ordinary cubic equation. We're only going to perturb x. So we can take y squared equals x cubed plus ax plus t. And we have different choices for a. So when a is equal to 0, then this family, here's the t line, and when t is 0, we have this cusp, and other than that, we have smooth fibers. And when a is not equal to 0, here's the t line. Well, then we have nodes exactly when x cubed plus ax plus t has a double root. So nodes occur in this family when x cubed plus ax plus t has a double root. And that's exactly when the discriminant of this cubic polynomial is 0, and it has to be degree 2 in t. I forget exactly what it is. I'll guess like 27 t squared minus a. I don't know. I don't know the coefficients anymore, but it has to be t squared because of the way symmetric polynomials work. So, in particular, we conclude. I can look up what it is. I know what it is. I know I'm out of time. It's minus 4 and minus 27. Thanks. So we get these two nodes, and that agrees with our Milnor number. We know that the topological degree is the rank, that's 2. So we have 2 and 2 nodes, and that's great. That's Milnor's theorem. And what the enriched version tells us is that the combination of fields of definition of these nodes and their tangent vectors has to satisfy the condition that when you add up the types, you get 1 plus negative 1. For instance, over F5, we have that 1 is equal to minus 1. So in a family, you can't have 1 split and 1 non-split rational node. But for F7, this is reversed. So you can't have 2 split or 2 non-split rational nodes. So you've obstructed certain kinds of arithmetic behavior in your family, and I'll stop. Thank you.
Questions?
Hi, do you know if this sort of arithmetic enrichment works for arbitrary, like complete intersection singularities rather than just hypersurface singularities?
I don't know a good notion of Milnor number for complete intersection singularities. So there are articles about. I think it's a tricky question over C. So I don't have an enrichment. That said, and there's some cool cool things over R. So the extensions of Milner number that are out there, I don't know how to make an enrichment, and they're also pretty, well, I find them tricky. Thank you.
Any further questions? If not, let's thank Kirsten again.